Hello everyone, so in this video I'd like to type a couple of loose ends and look at some terminology involving derivatives that doesn't get mentioned anywhere else. So one thing is that with derivatives there are lots of different pieces of notation that all mean the same thing. So unfortunately, if two different people supposedly invented calculus and they had a bit of a war over who invented what, you're inevitably going to get different terminology. So if we have a function, last time we used the terminology f prime of x. Okay, if y is equal to f of x, that's sometimes called y prime or dy over dx or df over dx or d over dx of f of x or df of x with a capital D. So all these are the same thing. And normally we're going to use dy dx of or f prime of x, but occasionally you'll see other things. And these symbols here, this d over dx and capital D, sometimes these are called differentiation operators because what they mean is anything that's to the right of them gets differentiated. So here we're saying d over dx of f of x means that the thing to the right of d over dx gets differentiated, so f gets differentiated. Similar here with d. The thing to the right of a capital D gets differentiated, so that f of x is getting differentiated. So as we said, those are differentiation operators. Sometimes if we have some complicated expression that we want to differentiate, rather than doing it all at once, we can write d over dx of the complicated expression, and then we can leave the actual differentiating until the next line. So sometimes I'll use that to split up the differentiation into multiple steps. Okay, and kind of a defect of the notation dy over dx is that it doesn't tell you where you're taking the derivative. It's just by default the derivative at x. Whereas with f prime of x, if we took the derivative at 0, we would write f prime of 0. So if we want to fix that with the notation dy dx, we use this vertical line and write x equals to denote we're taking the derivative at some particular point. So f prime of 0 would be dy over dx, and then this vertical line means evaluated at, say, x equals 0, or x equals whatever point you're interested in, just to specify where we're taking the derivative. Okay, a couple of other pieces of terminology is saying a function is differentiable and not differentiable. So all it means for a function to be differentiable at a point is that the derivative exists at that point. So remember, if we go back to how f prime of a was defined, we said f prime of a is the limit as h goes to 0 of f of a plus h minus f of a divided by h. If it does exist, then that point is the derivative and it's in the domain of the derivative function. If not, then there is no derivative. So we say f is differentiable if this limit exists. And f is differentiable in an interval if it's differentiable at every point of that interval. So sometimes you might be asked, what is the domain of the derivative, or where is the function differentiable? It's the same question. So you want to figure out all the points where the function is differentiable. So for instance, here is a simple example, f of x equals absolute value of x. So if you think back to the graph, right, it's a kind of V shape. So everything is good to the left and to the right of the origin, but at the origin, you have this kind of corner. So you might suspect it's not differentiable there. And that is the only place where it's not differentiable. So everywhere else it is. For instance, if x is bigger than 0, then the absolute value of x is just x. Taking the derivative is the same as taking the derivative of x. It's going to be 1. Similarly to the left. But what about at 0? Let's try to check what happens at 0. So if we want to know what happens at 0, we have to go back to the definition. So we look at f of 0 plus h minus f of 0 divided by h. Go back to the definition of derivative. Make sure you remember that formula. And if we plug everything in here, so f of x is the absolute value of x. So we have f of h, that becomes absolute value of h. F of 0 is 0, and h just gets copied. So this becomes absolute value of h divided by h. So we want to know if this limit exists. And remember that the absolute value is really a piecewise defined formula. So the absolute value of x is equal to x if x is bigger than or equal to 0, and it's minus x if x is less than 0. So whenever I have a piecewise defined function, I can try to take the limit by considering separately the one-sided limits. So if we look at the right-sided limit, say let's suppose that h is bigger than 0, then the top is just going to be h, the bottom is still h, this is 1, and it's constant 1, so the right-sided limit is going to be 1. Whereas if we go on the left, then for the left, if h is less than 0, absolute value of h is defined to be minus h, because the absolute value is supposed to be the positive part. So if we have a negative number and we want to get the positive part, then we have to reverse the sign. So the absolute value of h then is going to be minus h. So we get minus h divided by h, which is minus 1. So in that case, the left-sided limit is going to be, sorry, not 0. Here it should be minus 1. So the right-sided limit is going to be 1. The left-sided limit is going to be minus 1. They are different, so the limit does not exist. Or in other words, the function is not differentiable at 0. So the absolute value x is differentiable on 0 infinity and minus infinity 0, but definitely not at 0. Okay, so another thing to talk about is higher derivatives. So higher derivatives are easy. We just keep differentiating. So, The derivative that we talked about is sometimes called the first derivative. Because that's what we get if we differentiate once. If we want to get the second derivative, we just differentiate twice, or we differentiate the derivative, right? We said that if f is a function, f prime, the derivative is again a function. So we can try to differentiate that as we did before. And we just keep going, we get all the higher derivatives. So the nth derivative we get by differentiating n times, and it has this piece of notation. So the second derivative we differentiate twice, the third we differentiate 3 times, and so on and so on. You can differentiate as many times as you like, or at least try to if the function is still remains being differentiable. So for instance, here is a simple example. F is polynomial x squared plus 2x minus 1. And then as you can check using the limit definition, f prime becomes 2x plus 2. And now you could check again with the limit definition, or you could notice that this is the equation of a line that has slope 2. So the derivative of that is going to be 2. So the second derivative of f is 2, right? The second derivative of f is the first derivative of f prime. And then if we differentiate again, well, you could check with the limit definition that the next derivative is 0, or, f double prime is a constant. So the slope of a constant function is just going to be 0. Okay, and once you get 0, if you keep differentiating, you keep getting 0. So all the higher derivatives are going to be 0. So with a simple example like that, eventually, we could just compute, it got easier each time. Eventually, the derivatives were all 0. That doesn't happen with other functions, right? Though that you have functions, you keep differentiating them, you keep getting non-zero things. Maybe it gets simpler, maybe it gets more complicated, but at least with polynomials, they get simpler as you differentiate. Okay, one last maybe thing to touch on is, as we said, that we start with the function f, and then when we differentiate, we get a new function f prime with its own domain. And then if we do that again, we get a new function f double prime. So all f prime, and f double prime, they're all functions and they're all different. They're related by being derivatives of each other, but they're still different functions. So they have different graphs. So we have to kind of one thing we're going to have to understand is, what does the graph about f say about the graph of f prime, or the graph of f double prime, and vice versa. So one thing we can say at the first derivative level is that if f prime is bigger than 0, remember that f prime was supposed to be the slope of the tangent of f. So if f prime is bigger than 0, then f has positive slope, which means the graph is going up. And similarly, if f prime is less than 0, the graph of f has negative slope, so it's going down. So here is a very crude picture. For instance, it looks like the graph of x squared. On the right side, the derivative is positive and the graph is going up, and on the left side, the derivative is negative. And as we move to the right, the graph is going down. So nothing too surprising. Maybe a little more tricky is the second derivative. So if the second derivative is positive, remember the second derivative is the derivative of the first derivative, f prime. So f double prime is the slope of f prime. So if f double prime if the second derivative is positive, that means the first derivative is increasing. But then the first derivative is supposed to be the slope of f. So that means the slope of f is getting larger and larger. So the slope of f is getting steeper and steeper. And then vice versa if the second derivative is less than 0, that means the graph of f is getting less and less steep. So for instance, here is a picture. And in both of the pictures, the graph of f is increasing. The graph of f is going up. So the first derivative is bigger than 0. But in the first picture, the graph of f is getting steeper and steeper, whereas in the second picture, the graph of f is leveling out. So in the first case, the second derivative is bigger than 0. In the second case, the second derivative is less than 0. So what the graph of f looks like depends not only on the first derivative, but also on the second derivative. You could have very different shapes. Okay, so today we talked about the terminology of being differentiable or not differentiable. It just means that the derivative exists, or the limit in the definition exists. Higher derivatives, you just keep differentiating. And then we have to be careful to get the right relations between the graph of f and f prime and f double prime. Okay, thank you. See you next time.